Okay, perfect. Here's another example of a base, barium hydroxide. No, let me take that out. Sodium hydroxide breaks down into Na plus and OH minus. Once again, the OH minus is the base doing its job, and so Na plus is the conjugate. Here's a slightly trickier example. This is definitely a base reaction, right? Because what pops out on the other end, on the OH minus side, is a base. OH minus indicates the base. And what's left of the NH3 is NH4 plus. So NH4 plus is the conjugate.
Wait, sorry, what is tricky about that?
So there's two ways to think about why NH3 is a base, right? One is that on the product side, you see an OH minus pop up, right? Which is what we expect from bases. But the OH minus didn't really come from NH3. NH3 didn't have OH to begin with. It came from water, right? So here is where we apply the other definition of base, which is accept H plus. What happened was NH3 stole an H plus from H2O, and that's why it's a base. Yeah. This is important to classify acids and bases as Bronsted or Lewis. I always forget which one's which, but it's one of these distinctions. Okay, so that's that. Be careful with polyprotic or polyhydroxy bases, which simply means an acid with more than one H plus to give, or a base with more than one OH minus to give, or more than one H plus to accept, depending on how you think about it. Here's an example. H2SO4 has two hydrogens to give up, right? And H2SO4 breaks up into two H pluses and SO4 2 minus. But SO4 2 minus is not the conjugate of H2SO4. That's the point that I'm trying to make. To get a conjugate, you need to do it one at a time. Here we have let H2SO4 give off both of its H pluses in one go. And then the resulting part is SO4 2 minus. If we do this step by step, so let's take our H2SO4 and break it up one by one. Let's take out an H plus like that. So that's the first step. And then we take the HSO4, which is capable of giving up one more H plus, and do this. Then we have our proper conjugates. This is the conjugate for that guy, and this is the conjugate for that guy. So the idea is one at a time. Okay. Right, let's talk about acid-base strength. You can have strong acids, strong bases, weak acids, weak bases. Or you can have neutral species, neither acidic nor basic. Okay. So if you have some kind of a compound, a species, let's say an acid or a base, and you look at its conjugate, they are like complete inverses of each other, both in strength and in acid-base nature. If the species was acidic, the conjugate will be basic. If the species was basic, its conjugate would be acidic. And if the species was weak acid or weak base, the conjugate is strong. And if the species was strong, then the conjugate is weak. Okay? So, higher the strength of the species, weaker its conjugate. Weaker the species, stronger the conjugate. So it's opposite both in strength and in acid-base nature. Okay, given that, let's exhaust all the cases. So you can have, I'm gonna say strong acid. No, let's start with weak acid. Weak acid and weak base. Weak acid will give off a relatively strong base, or let's just say basic conjugate, because even though the conjugate is a stronger base than the acid, it's still not like super strong acids and super strong bases. Weak base will give off an acidic conjugate. Okay, now I'm going to make the leap. If you look at strong acids or strong bases, it is true that they will give off weak bases and weak acids as conjugates, right? But because the acids and the bases that we're talking about are so strong, the conjugates are extremely weak. So weak that you can approximately say that they're neutral. Okay, so strong acids and strong bases yield neutral conjugates. Any questions so far? All right. All right, so I'll leave it to that. And now the rest of the chapter is basically focused on these three things. Oh, before I get to that, let's talk about Ka, Kb, pH, and pOH. So let's start with Ka and Kb. Ka is the equilibrium constant for an acid. Kb is the equilibrium constant for a base. And they're always related like this. If you take Ka and you multiply it by Kb, you get 10 to the negative 14. So that's the first one. This is the concentration of H+. This is the concentration of OH-, i.e. the molarity of H+ and the molarity of OH-. And similarly, if you multiply the molarities, you get 10 to the negative 14. Now, instead of dealing with these quantities, you can also deal with their P counterparts. So instead of Ka, you can have pKa, pKb, pH, and pOH, right? And you should understand P as saying negative log. So pKa is negative log of Ka. Yeah, John.
I'm sorry, really quickly, what's the Ka and Kb again?
It's the Ka is the equilibrium constant for an acid. Kb is the equilibrium constant for a base. Yeah. So if you're looking at an acid dissociation reaction and you set up the equilibrium expression, you set it equal to K. That K should be acid K because it was an acid dissociation reaction. we give a lot of subscripts to K depending on what the situation is. If it's acid dissociation, it's A, base dissociation, B. In chapter 15, you'll see for solubility, it'll be KSP. Another thing called complex formation will be KF. It's just the same thing in different contexts. Similarly, PKB is the negative log of KB, and in the very same way, pH is the negative log of H plus concentration. POH is the negative log of OH minus concentration. And now if you add up as opposed to multiply the P values, they add up to 14 in each case. Any questions? Okay. We'll use these equations when we do some questions down the line. Okay. Now, the rest of the chapter is just going to be calculate the pH in this case, this case, this case, this case. And here's the organization of the chapter. Well, first, so calculate the pH. We'll start with looking at strong acids or strong bases separately. Calculate the pH of a strong acid, calculate the pH of a strong base. Done. That's the simplest case. Then we'll graduate to weak acids, weak bases. So either weak acid or weak base. Third, we'll talk about the pH of the conjugate counterparts. Right? Because weak acids and weak bases give off conjugates that themselves are acidic or basic. So what is the pH due to those counterparts, those conjugates? And conjugates usually are parts of different salts. So another way of reframing this section is to say, calculate the pH of a salt. And then the last one is to combine strong acid with weak base, or combine strong base with weak acid. And this is titration. Not only are you mixing acids and base, this is a neutralization reaction, right? But you're mixing acids and bases of opposite strengths. Strong with weak, strong with weak. Okay. In each of these cases, let me just say which ones involve ice tables and which ones don't. And here's an easy way to remember that. Anytime you have a strong species involved, there will be no ice table. It is very straightforward. Or let me say no true ice table. You might still write down an ice table for like a fake ice table. No true ice table. Here you would have an ice table because it's not strong. Conjugates are not strong either, so you will have an ice table. And then lastly here, you'll usually have two ice tables. The first one is never a true ice table. And the second one might be a true ice table. But okay, what I mean by true ice table is an ice table where you have X values, where you have variables. That's what I mean by true ice tables. If it's just for bookkeeping, like all of it is just numbers, that's not a true ice table. All right, so let's get started. Strong acids, strong bases. The idea with anything strong is that they react, they dissociate or react completely. That's the basic idea, and then that's it. There's nothing else. So for example, here's a question. Calculate the pH of, say, A, 0.5 molars NaOH, B, 0.5 molar HI, and C, 0.5 molar BaOH2, and D, 0.5 molar H2SO4. Oh, and one more thing. You need to memorize the list of strong acids and strong bases to distinguish what's strong and what's weak. Okay, cool. What happens to NaOH? NaOH does its nice thing of fully dissociating. So if you start with 0.5 molars of NaOH, it will break down into, all of it will break down into Na plus and OH minus. And that's what you get. We're interested in the concentration of either H plus or OH minus. And here what we have is the concentration of OH minus. Our question is to calculate pH, but we have nothing that relates to H plus. All we have is OH minus. So we'll always, for bases, use this intermediate step. You first calculate the pOH by taking the negative log of the OH minus concentration. And then whatever number you get, you use the pH plus pOH equals 14 rule to calculate your pH. So let's say that this comes out to some number that's going here. All right, Jonathan, break up HI for me.
H plus and I minus.
And I minus. So if this was 0.5,
They would each be 0.5.
0.5 and 0.5, and this goes away. Yep. And so what would the pH be?
It would be negative log of 0.5, right?
Yeah, and nothing else because we have H plus directly in this case. Okay. All right, Jonathan again. What's special about BaOH2? What's the trouble with this one?
It becomes Ba2 plus OH minus. Is that what you're looking for?
A Ba2 plus and what?
OH minus.
But there's two of them.
2 OH minus?
Exactly. So if this was 0.5,
that would be 0.5, and then that would be 1. Sorry, it'd be 1.
Exactly. Because of the coefficient, it doubles. And so OH minus is going to be 1, which means that POH is going to be negative log of 1, which is some number. And then you do 14 minus to get your pH. Cool. Same thing here, but for an acid, right? So 2H plus SO4, 2 minus. If this was 0.5, this is 1 and 0.5. So H plus concentration is 1, and so pH is just the negative log of 1. And you're done. All right, that's all there is about acids, strong acids and strong bases. Okay. Move on to weak acids and weak bases now. Let me just title this section as weak acids, weak bases. It's a very simple equilibrium problem. Calculate the pH of, say, 0.5 molars acetic acid, so CH3COOH with Ka, let's just say 10 to the negative let's say the 10 to the negative 8. B 0.5 molars. What's a weak base? I'll just make this up. C6H5NH2 with Kb as 2 times 10 to the negative 7. Okay. All right, so the idea is very simple, right? You just write down the reaction and write down the ice table and go from there. Okay, so here's your acid, CH3COOH. It dissociates into H plus because it's an acid, and what's left of the acid, which is CH3COO minus. And then you have your ICE, initial change equilibrium. So initially we've got 0.5 molars of CH3COOH. And initially all of the acid is undissociated. So there is no H plus or the broken piece to begin with. It's all 0.5 molar undissociated CH3COH. As we let the acid dissociate, some of it, so let's say minus an X amount of it does that, so plus X and plus X. The idea is very simple. In the equilibrium, in the change row, reactants get negative signs, products always get positive signs, and coefficients matter. If there are any coefficients, include them. Equilibrium is just initial plus change. So just add up the two rows. So this is 0.5 minus X, X, and X. Then set up the equilibrium expression, products over reactants, like we saw in chapter 13. X times X over 0.5 minus X. And then set this equal to the equilibrium constant. Since we were dealing with an acid dissociation, it would be Ka. All right, so that's X squared over 0.5 minus X equals 10 to the negative 8. This is a quadratic equation. Yeah, I think I covered small x approximation in chapter 13. If you saw, yeah. So we can do small x approximation here, right? Ka is small enough. So take out any x's that are being added or subtracted from a number. Example, that one. And now your equation becomes a simpler x squared over 0.5 equals 10 to the negative 8. And if you simplify for x, square root of 0.5 times 10 to the negative 8. Great. Which means that the equilibrium concentration of H plus is X. So That's what we have just found. So now all you need to do is take the negative log and you get your pH. And we're happy. Any questions? All right, let's do the second one. C6H5NH2. This is a this is an H plus absorbing kind of base. When you have that kind of base, you need water to make its basic nature shine through. So if you have a base that doesn't have an OH in it, add it to water. And so it will steal an H plus from the water and become that. And you're left with an OH minus at the end. That's what's left of the water. Cool. All right, so ICE. Water is a liquid. It never enters the equilibrium expression, so we can cross that out. And the business as usual. This is 0.5. Nothing has dissociated in the beginning, so 0 and 0. Minus x plus x plus x. And so 0.5 minus x, x, and x. Very similarly, setting up the equilibrium expression, products on top, x squared over 0.5 minus x equals kb this time. 2 times 10 to the negative 7. And you can do small x approximations, same as before, 1 times 10 to the negative 7. Take the negative log. What would the negative log give you this time, Pavel? pH or POH?
In this case, you're still getting the pH. I know you have OH in the OH. The pH, if I'm not mistaken.
Let's see. What does X represent in the ice table? OH minus, right?
I thought it represented like the amount of what is that compound? C6H5NH2.
Yeah, that too. But we're always only interested in either H plus or OH minus. Right? If you have your H plus value, you get pH. If you have your OH minus value, you get your POH. And of the two species of interest, OH minus is what corresponds to X. So if you take the negative log of that concentration, you get POH. And then you do 14 minus to get your pH. Okay. Yep. That's all there is to it. And that concludes the second section. Now let's move on to salts. I'm going to use these as our conjugate, CH3COO minus and this big guy. Okay, here's a question. So pH of either, now we're talking about conjugates or salts. So question, find the pH of a solution that is 0.5 molars in NaCH3COO where Ka is given by the same as before, which was, I made it 10 to the negative 8. And B, 0.5 molars in, let's see, C6H5 NH3 hold on, C6H5 NH3Cl. And let me change the first question, actually. Let me make this barium acetate, BaCH3COO twice. And let me elaborate that Ka of acetic acid is 10 to the negative 8. And then down here, Kb of C6H5NH2 is what it was before, 2 times 10 to the negative 7. Okay, so this is like the flip question. Now, your salt, every salt is 2 conjugates. That's what a salt is. When you have 2 conjugates, one from one acid, one from a base, come together, that's what we call a salt. So the first thing to do is to break up your salt into its respective conjugates. Okay, so let's do that. We have our BaCH3COO twice. This breaks up into Adam.
Okay, that would be BH CH3COOH.
Yes, Ba and CH3COO to COO, right?
Oh, I see. Yeah, right.
And 2 of them. Because there's 2 of them. And of course, put the charges on, 2 plus and CH3COO minus. So this is what it came from. And then the second thing is to figure out which of the 2 conjugates are pH active. You know what I mean? Which of them are non-neutral? Because remember, conjugates can, or substances, conjugates can be either, where was it? Conjugates can either be basic, they can be acidic, or they can be neutral, right? There's no point drawing out an ice table for a neutral conjugate. It will not do anything to the pH. So all you care about is to put your finger on the acidic or basic conjugate only work with that conjugate. That's the idea. But what is our algorithm for figuring out what constitutes a neutral conjugate, an acidic or basic? Is to look at the acid or base that it came from. Right? So we will do this reverse engineering here. Ba2 plus. So the way to reconstruct the acid or base is to basically opposite charges. If you have a positively charged conjugate, pair it up with OH minus. If you have a negatively charged conjugate, pair it up with H plus, opposite charges. So Ba2 plus, Jonathan, what would you pair it up with?
I would pair it up with OH.
OH. And how many?
2. So BaOH2.
Strong acid or weak acid? Or base?
I would say strong base.
Strong base. It should be in your list of strong acids and strong bases. Cool. So what does that tell you about Ba2 plus as a conjugate? Acidic, basic, or neutral?
It's acidic.
It is acidic, but exceedingly weak. So much so that we call it neutral.
Oh,
Right? Conjugates of strong species are always neutral. Cool. So Ba2 plus is not pH active. We don't care about Ba2 plus anymore. Which means the other one should be pH active. But let's just check because sometimes, and this is a trick question that they like to give, they'll give you both conjugates as neutral. Example, NaCl. Na comes from NaOH. Cl comes from HCl, both of which are strong base, strong acid. So this is neutral and this is neutral. Can you guess what the pH of a solution of NaCl would be?
guessing it would be like 7.
7. Because
Right.
it's, yeah, exactly. That's why when you swim in the ocean, you don't get acid or base burns, because NaCl happens to be a neutral salt. Okay. Great. Yeah, so just for completeness, this came from CH3. It's a negative ion, so I'm going to pair it up with the positive CH3COH, which is a weak acid, so we know that the conjugate is basic. All right. So let's take that. Let's take our conjugate, our pH active conjugate, which is CH3COO minus, react it with water, right? Because this base here doesn't seem like it has any OH in it. So it's the H plus absorbing kind of base. This will absorb an H plus to become CH3COOH, leaving behind OH minus from the water. Is this part clear? Okay.
So here, the H2O is acting as like both a base and
H2O is acting as a an acid.
because I'm thinking it donates a hydrogen, so it acts as an acid, but
Yep.
then it releases an OH, so that's acting as a base.
No. That is already implicit in, okay, so no. You are touching on something very important, and that only happens with water, by the way.
Right.
OH minus is the conjugate of H2O here. It's what's left of the water after the water has done its job of being an acid.
Right.
Yeah, but you'd never want to think of water as an acid or base. No. You just look at the other thing. Okay, so is this an acid dissociation reaction or a base dissociation reaction? Base, right? It's very simple. You look at what pops up on the other side in terms of H plus and OH minus. Here it's an OH minus. So this is a base dissociation reaction, which makes sense. All right, so now let's put in our values. And this is the reason why I changed question A at the last minute. This is 0.5. So what is the concentration of Ba2 plus? 0.5. What about this guy? 1. You double it. Don't forget to, yes, coefficients matter. So it's 1 and not 0.5. Okay. Water, again, don't care. 0 and 0. The usual minus x plus x plus x. 1 minus x, x and x. So if you set it up, x times x squared over 1 minus x equals Ka or Kb? Kb. No, you're right. Because it's a base reaction. Base reactions get Kb. Acid reactions get Ka. Do we have Kb in the question? No, right? I purposely gave you the opposite, Ka. Well, you know how to interconvert between Ka and Kb. Yes, Pavel, go ahead.
The product of Ka and Kb should be 10 to the power 14.
Negative 14.
Yeah, negative 14, I'm sorry.
Yep, exactly. So you can solve for Ka, divide by Kb, which is... No, we want Kb, divide by Ka, 10 to the negative 8, just 10 to the negative 6, I think. Yeah. Cool. Let's get rid of that. Small x approximation. X is the square root of 10 to the negative 6. If you do the math, it comes out to 10 to the negative 3. And so, if I take the negative log of 10 to the negative 3, what do I get? pH or POH? Grace?
Sorry, what did you say?
So if I take the... Okay, let's think about it this way. What is X correspond to? Is it the concentration of H plus or concentration of OH minus? Looking at the ice table.
It's the concentration of OH minus.
OH minus. So if I take the negative log of that number, what do I get? pH or POH?
pH?
Let's see. This was about OH minus, right?
Yeah.
Well, POH.
Okay.
They match up. The negative log of OH always gives you POH. The negative log of H gives you pH. Okay, cool. And then lastly, Alexandra, how do I go from POH to pH?
You subtract 14 minus that number.
That number. Very good. Done, done, done. All right, so that's it. Right, now let's run another dry run with part B. Same deal. 0.5 molars. It was C6H5NH3Cl, and I gave you Kb as this value. All right, break this up for me, somebody. Pavel, what does this break up into?
That will break up into what is that compound called? That is what's the nitrogenous alcohol? I mean, that's an ammonia compound. C6H5NH3 plus and chlorine minus.
Okay, I'll write down its name. It's called aniline chloride. Aniline chloride. Another way to this is from OChem. Another way to write its name is benzoyl chloride. Nope. Benzoic acid, benzoyl. Amino. I don't know, but it's aniline.
It's actually a benzene with an NH2, and when it's NH3, it has it's a protonated aniline. So it would be C6H5NH3 plus,
Exactly.
and chlorine minus.
Exactly. That's all. That's exactly what it is. Yeah, and if you have a benzene with an NH2 group on it, that's called aniline. Aminobenzene is aniline. Yeah, aniline chloride. Cool. So it's that and that. Which one traces back to a strong acid or strong base? Jonathan?
The C6H3NH3 plus would be the conjugate of a strong acid because it would have donated an H plus.
That, right? Or sorry, let's it's a positive, so let's pair it up with a negative, which is OH minus. Right.
Okay, so it's the conjugate acid, right?
This is okay, so this is the base and this is the conjugate acid of that. This is the conjugate.
Right.
Okay. What did Cl minus come from?
HCl,
HCl. Strong or weak?
strong.
So what about Cl minus?
It would be neutral.
Neutral, exactly. Chances are the other one is not neutral. Not neutral. And here's how you know whether this one is a strong acid or strong base. Basically, you have a list of acids and bases that you need to memorize or will be given to you on the exam or whatever. If something looks weird and doesn't fall into that table, chances are it's weak. Here's another way to look at it. This is the Kb value of this base right here. Is that a big value comparatively or a small value?
Small.
For
Small.
base, it's relatively large value.
Say that again?
For a weak base, that's a relatively large value.
No, it's pretty small, even for a weak base. Oh no, for a weak base, it's a relatively strong. Yes. But as far as bases go, it's a pretty small value. Okay, yeah. No, but it definitely puts it square in the range of weak bases. All right. So what would be the nature of the conjugate? Acidic or basic? Got to flip.
I'm sorry, are we talking about the Cl?
No, Cl you said is neutral, so it's not acidic or basic.
Oh, right. No, yeah, before we said it was the C6H3NH3 plus was the conjugate acid.
Acid, yes. Since this is weak base, that's got to be the acid. Yeah. And if you haven't figured that out, no worries, because when you write down the reaction, it should, you should see it. All right, let's react this with water. You can think of this as having an H plus to give off. So that becomes C6H5NH2. And it passes that H plus on to H2O, making it H3O plus. H3O plus is an alternate version of H plus, the same thing. So like instead of taking the negative log of H plus concentration to get pH, you can take the negative log of H3O plus to get pH. Same deal. All right, any questions in what I have written so far? All right, what is the concentration of C6H5NH3, given that we're starting with 0.5 of this? Pavel?
I would think that once the species break up into their conjugates and bases, you would have 0.5 molar of each.
Exactly. The ratios are all 1-to-1. As opposed to up here where it broke up into two pieces for CH3COO minus, which is why we doubled it. Right. Okay, good. 0.5. Once again, water, don't care. 0, 0. Minus X plus x, x, and the usual from there, 0.5 minus x, and x. And so what you get is, okay, Ka or Kb?
Ka.
Ka, because this is an acid reaction, which I do not have. They never, ever give you the K value in salt questions that you actually need. They'll always give you the reverse, which is what I have done. Okay, so 2 times 10 to the negative 7 is the Kb. All right. Grace, do you remember how to convert Kb back to Ka?
It's gonna Ka times Kb is gonna be 10 to the negative 14.
Exactly. Kb 10 to the negative 14. What do I do next?
I mean, solve for Ka.
Exactly. Yep. That's exactly what it is. I think this thing comes out to 0.5 times 10 to the negative 7. I think. Okay. Okay, good. 0.5 times 10 to the negative 7. Small enough so you can do a small x approximation by, and so x equals 0.5 times 0.5. Just some number. Okay, since it's an H3O plus or H plus concentration, all I need to do is take the negative log and we're done. Okay. Great. Moving on to the last and most important section, titrations.
So Abdullah, really quick, what time does this go until again?
12:30.
Okay, awesome. Thank you.
12:30. Yeah, okay. So titrations. And okay, yeah, for titrations, yeah, I've refined teaching titrations over recitations, and I think this is as, at least for me, as good as it gets. And here goes. Remember, in titration, we have a weak species reacting with a strong species, and the species are opposite in nature, right? If it's weak acid, then strong base. If it's weak base, it's strong acid. So we're just going to talk about titration as so strong plus weak gives. At the end of the day, the two reacting things are acids and bases, right? What is the acid-base general reaction? Anybody?
Acid plus base gives like a salt plus water. Is
Salt?
that? I might be thinking of something else.
Nope,
Yeah.
you're right. Salt
Okay.
and possibly water. You don't get water every time. But we don't care. It doesn't enter the ice table anyway. All right, so that is exactly what it is. I'm just going to move it over here and then duplicate this. Twice. Okay. So we're going to look at 3 possible cases for our ice table to be in. Command C. Okay. And these are the only 3 possibilities that you can have for titrations. Okay. There we go. Okay. You can either have, first case, more of the strong species, so big number here, and a little bit of the weak, right? So this is the case where the strong dominates, the strong is more than weak. Or you can have the flip version, little bit of the strong, a lot of the weak, or you can have them in exactly equal amounts. Okay, so just based on this, let's complete the rest of the titrations of the ice table. I'm just going to cancel out H2O in each case. Case 1, the strong one dominates. Remember, the idea is that the reaction goes to completion, right? Which means the reaction goes as far as possible until one of the reactants run out. That's what strong species do. Which one is the limiting reactant here? Which one will finish first?
The weak.
The weak one, right? Because it's present in the lower amount. So the reaction will proceed for as long as it takes for the weak to finish, which means that all of the weak species is going to get used up, right? So that is our X. So we basically know what our X is. X is the amount of the weak stuff. And so now look at what happens at the end. The strong species, there is some non-zero number that survives at the end. The weak species becomes 0, and you have a little bit of the salt. Let's look at the surviving species. You have the strong species that survives at equilibrium, and you have some salt that survives at equilibrium. In addition to water, we don't care about water. If one of the surviving species is a strong species, it dominates again. So all of the acid or basic nature of this solution is going to come almost entirely from the strong species, right? And so you forget about the salt and you just focus on the strong species and calculate the pH of the strong species of this molarity at the end. Know what I mean? And so case 1 of titration breaks down into an earlier case, pH of strong acids or strong bases, which we've seen how to do before. Now the surprising thing is all 3 cases of all 3 cases of titration break down into something simpler, something that we've studied before, except one of them because I forgot to introduce it. No big deal. All right, so this just becomes that. You do the first ice table, you see what molarity of the strong species survives, then you calculate the pH or pOH based purely on that, and you're done. You forget about the salt. Strong dominates. All right, so that's case 1. Case 2 is the flip version. This time, what is the limiting reactant? The strong species, because it's present in the smaller amount. Okay, so Let's get rid of that. Let's get rid of that. This is 0 to begin with. Yep. So this is 0. Something survives here. It's a non-zero subtraction. And a little number here. Now, what survives is weak species and salt, which contains the conjugate of the weak species, correct? Because that's what salts are. So essentially, this is a weak plus its conjugate mixture, right? You have a mixture of weak and its conjugate. This combination is what we call buffer. When you have a weak species and its conjugate simultaneously present to begin with, that's what we call a buffer. And for buffers, you use Henderson-Hasselbalch equation. It's very simple. It's plug and chug. And there's two variations to this. If you have an acid, weak acid, plus its conjugate, then you use this guy, pH equals pKa plus log of, and I like to write it like this, concentration of the conjugate divided by concentration of the acid. If you have a weak base and its conjugate, then literally just change the whole formula to its basic counterpart. pH, the basic counterpart for pH is POH. The basic counterpart to pKa is pKb. You still have your conjugate, but now you have base. That's how I remember the Henderson-Hasselbalch equations. Which means that if you have a weak base and its conjugate, you first calculate your POH using the equation and then do 14 minus to get your pH. It's always the same dance with bases. Okay, so that's that. Last case, when you have equal amounts of strong and weak, both are limiting. And so all the strong gets consumed, all of the weak species gets consumed, and all that's left that's of importance at the end is the salt. Have we seen calculate pH of salt questions before? Yes. Yes, we have. So now this becomes pH of salt case, which we know how to do. Take your salt, you break it up into its conjugates, and you find the pH active one. You draw an ice table and go from there. All right. So we'll end today's class by discussing an example from each case. By the way, case 3, when you have an equivalent amount of acid and base, that's called titration to equivalence. This is equivalence titration. Yeah, equivalence titration. All right. Now, here's a complication with titration questions. And I'll illustrate that with a very simple example. Titrations involve mixing. Mixing is bad for molarities. Right? So for example, if you have, if you combined 300 milliliters of 0.5 molars CH3COOH with 250 milliliters of 0.4 molars HCl, right? You might be tempted to draw your ice table, give salt and water, blah, 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 whatever, and then immediately put, CH3COH is 0.5, HCl is 0.4, and go from there. But that's not correct. And that's the only problem with titrations. It's that it involves mixing, and when you mix, the overall volume changes, which makes the molarities change. There's dilution happening. Mixing involves dilution. So what's happening here, the 0.5 refers to the acid alone, and the base refers to, so these numbers refer to the acid and the base alone. What the ice table here is concerned about is mixed molarities. When you combine these, you get a bigger volume, and the molarity of the acid and the base change because each base and acid has access to a larger volume now. So the molarities change. One way to get around this problem is to calculate the new molarity of the acid and the base in the mixed solution using the dilution formula, M1V1 equals M2V2. But I feel like that's a lot of work. What you can do instead is do titration ice tables, or at least do the first ice table in millimoles instead of molarities, big M. That way you circumvent this problem. Millimoles you get by multiplying your milliliters by the molarity, right? So if we go back up here, instead of using 0.5, let's look at how many millimoles of CH3COH we've got. 300 times 0.5, which is 150 millimoles. How many millimoles of HCl have we got? This times that, which is 100. Yes, 100. And then go from there. Always do your first titration ice table in millimoles, not molarities. If you need a second ice table in a titration question, you must do that in molarities. Very important to remember. Which means to go from the first ice table to the second one, you need to convert your millimoles back to molarities. But I promise you that is easier than converting both of your initial molarities, individual molarities, to combined molarities using dilution formula. Okay, so let's put all of this into action and end it there. Here goes. Calculate hold on. A 0.1 molar HCl solution Yes. Moles per, yes, exactly. 0.1 molar HCl solution is titrated with, titrated is just a fancy word for saying mixed with, 0.5 molars. Let me take out the HCl and replace it with NaOH. 0.5 molar CH3COOH. Okay, so immediately off the bat, tell me what is the strong species here, what's the weak species? Pavel?
Well, NaOH is by definition a strong base.
Correct.
So that would be the strong species.
Yep. Chances are the other one is the weak. And it is. Yes. And I'm also going to give you that the Ka of CH3COOH is, let's just say, 2 times 10 to the negative 8. Okay. Calculate the pH of the solution when part A, let's see, (600 milliliters of NaOH is titrated with 100 milliliters of CH3COOH. That's part 1. B, let's switch places, 100 mils of NaOH is titrated with 600 mils of, or let me just say 100 with 100. That's fine. And lastly, and this is often how they pose this question, 250 milliliters of CH3COOH is titrated to completion. Notice in parts A and B, I always give you 2 volumes. Volume of the strong and volume of the weak. In part C, however, I'm only giving you 1 volume. And that's what they usually like to do in completion type questions. And I'll tell you how to figure out the other volume. It's also M1V1 equals M2V2. All right, so let's start with the first one. So we have NaOH reacting with CH3, whoops, reacting with CH3, COOH to form. Can someone tell me what the salt here would look like?
CH3COO. I'm sorry, NaCH3COO.
Yep. That's basically you combine the leftovers of each species, right? What's left over here, Na plus. What's left over here, CH3COO minus. Yep. And so it's NaCH3COO. And then this thing gave off an OH minus, this thing gave off an H plus, so that's H2O. Great. We have our reaction. ICE. This is our first ice table, so we're gonna do this in millimoles. Alexandra, how many millimoles of NaOH do we have?
Millimoles. I'm gonna be real, I don't know.
Okay, so remember how I said millimoles is milliliters times molarity.
Yeah.
That's it.
So it's gonna be 600. No.
Correct. 600
Oh,
milliliters.
600 times 0.1.
Correct.
So that's it.
Yep. 60. All right. Fill in the rest for me. What about CH3COOH?
Oh, still me?
Yep.
Okay. So the rest is going to be 100
Yes.
times 0.5,
Correct.
which is 50.
50. Exactly. What about this guy? NaCH3COO. What is its initial millimoles? Yep, in the beginning, the reaction hasn't taken place yet, so no salt
Right.
has formed. Okay, good. Awesome. Still Alexandra. What is the limiting reactant here?
The CH3 COOH?
Yes, so what would this row look like?
60 minus
But yes, minus x plus x, but we know what our x is. The reaction goes to completion, so the lowest thing runs out.
Oh, got it. So that
So-
one's is minus x, x.
Yes, but
Oh, 50. Minus 50, minus 50, 50.
exactly. Yeah, you use the lowest number. There's some asterisks here involved because you can have coefficients and that changes things. But anyway, we'll not think about that for now. Yes, okay. All right, so what's left at the end, Alexandra?
We have 10 NaOH, 0 CH3, and 50 NaCH3.
So in words, tell me what survives at equilibrium.
In words, the Na, I actually don't know. I don't know what to say.
Yeah, NaOH. Yeah, you're right.
But the NaOH, is this is the base?
Yes, it's the strong base.
The strong base and the product survive.
Yes. What is this product called?
That product is called. It's coming up right now.
Okay.
It's called. I don't know. I don't know. What
Okay,
it's called.
let's see. Let's see what it's called. Right there.
Oh, the salts. Of course.
Exactly. That's what a salt is. Yes. So you have strong base and salt. All right, so you're good. Now, we have a strong species that survives. So we ignore everything else and we run with our strong species. Okay. So we have 10 millimoles of NaOH. Usually, to do any kind of calculation for pH or pOH, you need the molarity. What is the molarity of NaOH here? Let's see. To calculate molarity, you divide millimoles by total milliliters. We know that we have 10 millimoles. What is the total volume in part A when the two things are mixed?
700.
700. There's 600 mils from here and 100 mil from there. Exactly. Could have chosen better numbers. Anyway, 10 over 70. Exactly. All right, so that's some number. What can I immediately calculate using this number?
Moles per liter.
Yes, so this is the molarity of NaOH. What can I calculate from that? My eventual goal is to hit pH.
Oh, you can calculate like the molarity of OH.
Yes, exactly. So you know that because it's a NaOH breaks up into Na plus and OH minus, that is indeed the molarity of OH minus. Cool. And so what can I calculate from that? Adam?
The POH.
Exactly. POH. And then do 14 minus and get your pH and you're done. Okay. That's it. Done, done, done. It's that simple. All right, let's play the same game with parts B and C and we'll be done.
Dula, fortunately, I do need to leave.
That's okay.
But
Yeah.
thank you so much. I'll make sure to review whatever notes you go over after this.
Yes, all good. All right, bye. All right. Coming up, part B. I'm gonna copy down the same equation: CH3COOH plus. Let me switch places because it doesn't matter how you write it. I just want to be consistent with my other questions. Plus water. All right. Grace, in part B, how many millimoles of NaOH do I have?
We have 10.
10, good. What about CH3COOH?
5.
50.
Or sorry,
But
50.
I know what you're doing in your head. Yeah, 50. Good. What about the salt?
0.
0, and this we don't care about. What is limiting here?
The NaOH.
Okay, so tell me what this would look like now. The change row.
10 minus X.
Nope, we never write X's in our... Yep.
Minus 10.
Minus 10.
Minus 50.
Yep.
Plus 10. And then it'll be 0. 40.
10. 10. All right, so what survives at the end?
CH3COOH.
Yep. And what was that?
What do you mean?
Strong base, weak acid, salt.
That's a strong acid.
Let's see. I think it's I've forgotten which one was what. Let's go back and see. So we had said that NaOH is the strong base and this is the weak acid. And it is the weak acid because if you look at your list of strong acids and strong bases, you won't find CH3COH. So by exclusion, you can figure out that it's the weak acid. Yeah, okay, cool. And what else is left?
And the NaCH3COO.
Which is what?
Your Conjugate
Conjugate?
acid.
Yeah, or salt. Okay, excellent. And now remember, in this case, we use Henderson-Hasselbalch because it is weak and conjugate mixture. That's what we call a buffer. And so we use the Henderson-Hasselbalch equation. And since it's acid and salt, we're going to use the pH equals pKa plus log of conjugate divided by acid. All right. First of all, what is pKa? That's something we need to figure out. Let's go up here. I have given you the Ka of CH3COOH is 2 times. Let me just make it 10 to the negative 6. Make that edit to the question. Ka of CH3COOH, make it just 10 to the negative 6. All right, so I have my Ka, which is 10 to the negative 6. Grace, tell me, how do I convert this into pKa?
Sorry, I'm blanking.
Do you remember what P stands for?
pH.
Nope, just the P
Oh.
part.
Okay.
Let's see. I think I said it all. Yeah, right here, all the way in the beginning. P is negative log.
Okay.
Right, so pKa is negative log of Ka. So if Ka is 10 to the negative 6, what's pKa?
One sec. 5.
Oh, is that what you got?
Yeah.
So this is what you're doing, right? Negative log of 10 to the negative 6?
Uh-huh.
Try it again. I don't think you should get 5. You should get something else.
Six.
Exactly. All right, so I'm just filling in the blanks now. pH equals pKa, which is 6 plus log of. Another note, Henderson-Hasselbalch can also work with millimoles instead of molarities. All right, so what is the millimoles of the conjugate, Grace? Looking at 10, good. And the acid? 40. That's it. That's the answer. You just put that in a calculator and that's it. That's your pH. Excellent. All right. Last part. Question says that you have 250 milliliters of CH3COOH, and that's all it tells you. All right, so one last time, I'm going to write down NaOH plus CH3COOH gives NaCH3COO plus H2O, just like before, ICE. All right, Alexandra, how many millimoles of CH3COOH do I have?
millimoles of CH3.
in part C.
Part C, okay. So we had 250 times 0.5, 125.
125. Excellent. Okay, okay. Oops, it's the other thing. Okay, so if this is 125 millimoles and this is a titration to completion, what would the millimoles of NaOH be?
Half? I don't know.
Remember, we have three cases. One bigger than the other bigger
Oh,
than
they're
one.
equal this time?
Yeah,
Oh, okay.
that's what equivalence is all about. Okay, so if you know the millimoles of one, you absolutely know the millimoles of the other. It's the same. Okay, and this is 0. Okay, so now we know what the millimoles of NaOH are, right? It's 125 millimoles. And what was the molarity of NaOH again? 0.1. Can we figure out the volume of NaOH using this information? Which is missing in the question, right? Yes, you can. Molarity is moles divided by volume, or another way of writing molarity is it's millimoles divided, so moles divided by liters, or millimoles divided by milliliters. So if you want to solve for milliliters, it's millimoles divided by molarity, which is 125 over 0.1, 1250. Does that make sense?
Yeah.
Cool. So that's how you fill in the blank in equivalence questions. You first figure out that, hey, the millimoles must be the same as the other one, and then using millimoles and the molarity, you figure out what the volume must have been for it to work. All right, perfect. All right, complete the rest of this table for me, Alexandra.
So if it's to completion, it's minus 125.
Yep. All right.
Oh, is it just 0?
Yep. And
Oopsies. 125.
125, exactly. And now tell me in words what survives at the end.
The salt.
The salt. And what part of the salt is important? As in, so this breaks up into Na plus and CH3CO minus, right?
Mm-hmm.
Which of these is neutral is basically what I'm asking. Where did it come from? Na plus. The strong species or the weak species?
The strong.
The strong species. So it must be
Strong. Neutral.
neutral.
That was my first instinct, yeah.
Yep. So we don't care about Na plus. We're just going to focus on CH3CO minus. This is the only case in titrations where you have a second ice table. All right, ice table number 2. And this is with your usual X's and everything. All right, so let's react this with water. It seems like it can accept an H plus to become CH3COOH. And so what's left is OH minus. Any questions about how I wrote down this equation? Right, so since CH3CO minus is the conjugate of a weak acid, it must itself be basic. And that's why in this equation it has absorbed an H plus. It doesn't have OH minus to give off, so it does the other thing, absorb H plus. The usual, what we've seen before. All right. Let's do our ice table. Remember, anything other than the first ice table needs to be in molarities. Okay, so let's figure out the molarities of CH3COO minus. Remember, it's millimoles divided by total milliliters. Alexandra? What?
It was. Oh, but we did. Oh, wait, hold up. Oh no, we had the NaOH one.
Mm-hmm.
Okay, millimoles was. Oh, it was the 125.
Exactly.
Divided by the 250.
Ah, that's only one of them.
Oh crap.
Here's the other one.
Oh dang, what is that? 1500?
Yep, 1500. That's why I'm emphasizing total milliliters. It's the sum of the two. Okay. All right, can you calculate that for me real quick?
Yeah, it's 0. Or wait, do you want it in the scientific notation?
Just
Okay,
regular
okay.
notation. Yeah.
0.083.
Perfect. 0.083. All right, business as usual. 0 minus x plus x plus x, just like you would do a solved question. X and x, and so x squared over 0.083 minus x equals Ka or Kb, Alexandra?
KB.
Mm-hmm. Because of that. Yep.
Mm-hmm.
Did I give you the Kb in the question? Nope. I give you the Ka, 10 to the negative 6. All right, so if Ka is 10 to the negative 6, how do I calculate Kb?
It was 10 to the negative 14 divided by 10 to the negative.
Just 10 to the negative 8. All right, let's do small x approximation, solve for x, and so you get this. Just some number. Okay, what can I calculate from here? pH or POH?
POH.
Excellent. And then you do 14 minus to get your pH, and we're done. Any questions? All right. Sorry for holding you guys 15 minutes longer, but this is, I think, a pretty comprehensive breakdown of the chapter. All right. I'll see you guys next week.
Thank you.
Thank you.
Have a great weekend.
Yep, no problem. Bye.
Thank you. Have a good one.
Likewise.